Hi, this is the first video in a unit called chemical bonding. Bonding is what holds one atom to another atom within a molecule. And it all has to do with the valence electrons in the atom. All right, there are three types of bonds that we're going to talk about. The first type is called an ionic bond. And the key here is that the electrons that are taking part in the bond are transferred, and you're going to create ions. Ionic compounds are made of metals and nonmetals. Now, a covalent bond is when electrons are shared, and that is with all nonmetals. And then metallic bonds are when electrons are free to move around over the metals, so the valence electrons are just kind of in a sea of electrons. And you're going to watch an animation of this with after this video. Okay, so sea of electrons is a way to describe it. They're just kind of free moving. Another way to describe them is that the electrons are delocalized. And what that means is that the electrons don't have any one place that they're staying. They're just kind of, free flowing. So the key words: ionic bonds, electrons are transferred. Covalent bonds, electrons are shared. And metallic bonds, which are used in metals, are seas of electrons, are free to move around electrons, or delocalized electrons. This video is going to be an overview of all of these types of bonding. Well, the bonding is between two different atoms. So doesn't it make sense that what's on the outside of the atom is what's going to be used in bonding? And that's exactly the case. And so it's our outermost electrons that are used in these chemical bonds. And if you remember, these are called our valence electrons. Now, we need to remember how many valence electrons the different families have. So let's review that. So here we go. The alkali family, or group 1A, they have one valence electron. One valence electron. Let's go next door. In the alkaline earth metals, they have two outermost electrons, or two valence electrons. We're not going to work with our transition metals right now, so let's move on to the boron family. They have three valence electrons. The carbon family has four. Nitrogen family, 5, you see the pattern. Oxygen family, 6. The halogens have 7. And then starting with the noble gas neon, they have 8 valence electrons. Helium only has 2, because that's all the electrons it has. Okay, so what are questions that you're going to get from something like this? We could say, hey, how many valence electrons does arsenic have? And the answer would be 5, because it's in this family. How many valence electrons does gallium have? The answer is 3. How many valence electrons does calcium have? It has 2. How many does barium have? 2. The reason that group members or family members have very similar chemical properties, it's because they have the same number of valence electrons. Okay, so you need to know how many valence electrons that these atoms have. All right, now there's something called a Lewis symbol. And the electron dot Lewis symbol is where you're going to show the valence electrons with a dot. And these dots are going to be around the symbol of the element. So let's go ahead and practice this. Let's draw the Lewis dot symbol for sodium. So the first question is, how many valence electrons does sodium have? Go to your periodic table. It's in this family. It has 1 valence electron. So the Lewis dot structure for sodium is easy. You draw the symbol Na, you draw 1 dot, and that represents sodium's valence electron. All right, let's go to magnesium. How many valence electrons does magnesium have? Here is magnesium, atomic number 12. It has 2 valence electrons. So what you'll do for magnesium is you're going to draw, well, it's unfortunate I have these bulleted here. Here we go. We'll draw magnesium over here. Here's 1 valence electron. And here's the second. All right, let's go to aluminum. Aluminum has 3 valence electrons, so the Lewis dot symbol would be the aluminum symbol. 1 valence electron, 2 valence electrons, 3 valence electrons. Next one is carbon. How many valence electrons does carbon have? It has 4. So we'll draw the symbol for carbon, and we're going to put one electron on each side of our symbol before we start to pair them up. And you'll see why later, why we do this. It has to do with forming bonds with other atoms. All right, nitrogen. Let's draw the Lewis dot symbol for nitrogen. Well, nitrogen has, let's see, 1, 2, 3, 4, it has 5 valence electrons. So for nitrogen, we're going to do 1, 2, 3, 4, 5 valence electrons. Oxygen, if you look at your periodic table, well, here, we'll go ahead and look at ours. Oxygen has 6 valence electrons, and so we're going to draw 6 electrons. So 1, 2, 3, 4, 5, 6 valence electrons. Chlorine has 7 valence electrons. Here are the halogen family, so 7 valence electrons, and here we go. 1, 2, 3, 4, 5, 6, 7. Okay, Lewis dot symbols. Again, it's just the symbol for the element, and each dot represents a valence electron. All right, now let's just talk briefly about ionic bonding. Ionic bonding are where the electrons are completely transferred. Metals like to lose electrons, because if they lose electrons, they could achieve an octet. And nonmetals like to gain electrons to have an octet. What is an octet? An octet, like the name implies, is 8 valence electrons. And we know that our noble gases have 8 valence electrons, and they're very stable and unreactive. And the other elements would like to achieve an octet in their outermost shell so that they can be stable and unreactive. Metals lose electrons, so metals would become positively charged. And nonmetals gain electrons, they form a negative charge. And what do we know about opposite charges? It's this theme that keeps coming up over and over in chemistry. Opposite charges attract, and that's what the ionic bond is. It's the positive and negative charges that are attracting to one another. And that's called electrostatic forces. Whoops, not spelling it right. Electrostatic force is the positive and the negative charge attracting one another. Okay, so we're going to look at ionic bonding a little bit later, but let's look at this sodium with its valence electron, 1, and chlorine had 7. And what happens here is if sodium were to lose its 1 valence electron, then, let's go to our periodic table. If sodium were to lose 1 valence electron, then it would have 10 electrons, and it would have an electron configuration like neons, and so it would be stable. It's not neon because it still has 11 protons in the nucleus, but its electronic structure is like neon, so it would be isoelectronic with neon. Chlorine, boy, it has 7 valence electrons. If it were to only gain 1, then it would have 18 valence electrons and be isoelectronic with argon. And so this is pretty much what I like to call a match made in heaven. Here's sodium, who's like, oh, I would love to get rid of this valence electron so that I can have my octet and be like neon. And chlorine is like, man, if I could just pick up 1 more electron, then I could have, an electron configuration like argon. And so sodium is like, hey, you want my electron? Chlorine's like, absolutely. And so what happens is our sodium now has a positive charge. The chlorine that gained that electron from the sodium now has a negative charge. Both of these ions are completely stable and happy, and they're sticking together, and that's the ionic bond. Again, ionic bonding creates ions because electrons are transferred. Okay, well, ionic bonding takes place between metals and nonmetals. And so I just wanted to review that. We started at the beginning of the year with this. We even colored the periodic table. with metals and nonmetals, but about 75% of the periodic table is metals. It's this whole left side over here. Okay, these are all of the metals. And then our nonmetals are here in purple, so they're on the right of the periodic table. And then there's this kind of line or staircase between the two. And those elements that border that staircase, they have properties of metals and of nonmetals, and we call them metalloids. Okay, so an ionic compound is made up of a metal and a nonmetal. All right, so here are some examples of ionic bonding. Sodium chloride, metal, nonmetal. Potassium bromide, metal, nonmetal. Magnesium oxide, metal, nonmetal. And aluminum sulfide, a metal and a nonmetal. Okay, covalent bonding. Now this is where electrons are shared, and it's between non-metals. And so let's go back and just look at our periodic table here. The non-metals, they're over here on the right side of the periodic table. Covalent bonding is where the electrons are shared. And we're going to spend a lot of time drawing structures of things that use covalent bonding. But for right now, just know that covalent bonding is where electrons are shared, and it's, a nonmetal with a nonmetal. So it's something like water, carbon dioxide. See, nonmetal, 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 nonmetal. Ammonia. Or these polyatomic, even though it's an ion, it has a charge, the atoms that compose, that make up this polyatomic ion are nonmetals, and they use covalent bonding. Okay, metallic bonding, and I'm going to have you watch another video after this one because it's animated and they do a really good job, but it's between metals, or within a metal. And this is where the electrons are delocalized, or a sea of electrons. Okay, so here's what we want you to be able to do after watching this video. Be able to look at a compound and say if it's using ionic bonding, metallic bonding, covalent bonding, and in some cases we're going to see that it will use both ionic and covalent. Okay, zinc chloride. Zinc is a metal, chloride is a nonmetal. So what type of bonding? Ionic. CH4 is methane, and there's no metal there at all. It's all nonmetals, so the bonding that is used is covalent, so the electrons are shared. Sulfur trioxide, no metal there, so it uses covalent bonding. All right, oh, hey, this has a charge. It's a positive charge. It's a cation. But let's look what makes up that cation. It's a nonmetal and a nonmetal. Ammonium uses covalent bonding. And then hopefully you know OH with its -1 charge is hydroxide. This is how you identify a base if it has an OH negative. And again, it has a charge, but the atoms are nonmetal, nonmetal, and so the bonding used here is covalent. And let's try this. Potassium, that's a metal. Hydroxide, OH, this is a polyatomic ion. Oh, and that polyatomic ion is all nonmetals. This is a case where there's ionic bonding between the potassium and the hydroxide, the metal and the nonmetal region, and within that OH, keeping that O bonded to the H, that polyatomic ion, nonmetal, nonmetal, there's a covalent bond there. So, potassium hydroxide has ionic and covalent bonding. Calcium chloride, metal, nonmetal, so it's ionic. Sodium nitrate. Sodium is a metal, so metal, nonmetal, we have ionic bonding, but again we've got that polyatomic ion nitrate. The bonds between the N and the O are covalent bonding. So we have ionic and covalent bonds. Now this is an alcohol. I know that OH, once you want to think that it's a base and that it's hydroxide, but there's no metal in front of it. This is all nonmetals. There's no metal present at all, so it is covalent bonding. Okay, we're going to practice this in class. So, summary. Ionic bonding has positive and negative charges, and you have a metal and a nonmetal. Covalent bonding is all nonmetals. This is where your electrons are being shared. And metallic bonding is used in metals, and that's where our electrons are delocalized. All right, now after watching this video, I want you to watch the next video on metallic bonding. All right, have a good night.